Today's notes are on limiting reactants. Before we get into the chemistry examples, let's do some examples of stoichiometry in the real world. Let's say that we want to make a peanut butter and jelly sandwich. And we look in our pantry, and what do we have? We have 4 slices of bread, an entire jar of peanut butter, and half a jar of jelly. So if I have all of this, which of those 3 ingredients is going to be what limits the number of peanut butter sandwiches I can make? And that would definitely be my bread. So my bread is called my limiting reactant because it is going to run out first. So then what would I have left over after I made my peanut butter and jelly sandwiches? I would still have some peanut butter left and some jelly left. Let's take a look at another example. Let's say that we're making s'mores and we have 24 graham crackers. We have an entire bag of marshmallows, but we can only find 12 pieces of chocolate. So if I wanted to make s'mores, which ingredient would limit the number of s'mores I could make? In this case, that would be my chocolate. So my chocolate would run out first, and it would limit how many s'mores I could make. So after I make my s'mores, what would be left over? I would have leftover graham crackers and leftover marshmallows. So now that we're familiar with the terms limiting reactant and excess reactant, let's take it to some chemistry examples. So let's define what a limiting reactant is. There are 2 ways you could think about the limiting reactant. And the first is it's the reactant that's used up in the reaction. So when we were making our peanut butter and jelly sandwiches, right, we were using up all of our bread and all of our chocolate. And because we used it all, it limited how many products we could make. So when we only had 4 slices of bread, we could only make 2 peanut butter and jelly sandwiches. The reactants that were left over at the end are called our excess reactants. So after we use all of our limiting and our reaction is done reacting, this is going to be the reactant that's left over. Now, in both of our examples, we had 2 excess reactants, but in general, most of our chemical reactions that we've done, we only have 2 reactants. So when we do our chemistry examples, most of the time, we're only going to have 1 excess. Now, in the real world, whenever we do chemical reactions, oftentimes we have 1 reactant that's going to be limiting because maybe it's more expensive, or we want to make sure that we use it all because that ingredient in itself might be like bad for the environment. And so our excess reactant is the one that's added to ensure that the other reactant is completely used up. For example, copper. Copper is pretty expensive. And so if we're doing a reaction with copper, we're going to put in a whole bunch of the other reactant to make sure that all of our copper gets used up so we don't waste it. So the excess reactant is going to be the one that's left over. And oftentimes it gets added to ensure that we use all of the other one because this excess reactant is cheaper and it'd be easier to maybe get rid of at the end, easier to recycle. So how do we find what our limiting reactant is in a chemistry example? So step 1 is to write the balanced equation. Then what we're going to do is we're going to take 1 reactant and we're going to convert it to the amount of the other reactant. And we're going to then see which one is going to run out. Now, whenever we convert to the other reactant, what this answer is it's how much of the reactant you need to fully react with the other. So we're going to do a lot of labeling of what do I have and what do I need. And if I have enough, then that thing is going to be my excess reactant because I have enough of it. So it'll be left over at the end. If I don't have enough, though, that means that that's the limiting reactant because it would run out before the other reactant. Once I determine the limiting reactant, I always want to start with the limiting reactant. Okay, so then I can do the limiting reactant and convert it to the product or maybe to the other reactant to answer the follow-up questions after that. We're ready to try an example. So let's read the problem. 79.1 grams of zinc react with 68.1 grams of hydrochloric acid. So let's start with our chemical equation. And the first step is that we need to balance this equation. So when I look, I see 2 hydrogens and 2 chlorines in the products, but only 1 in the reactants. So I'll start by putting a 2 in front of the hydrochloric acid, and that should balance it. Now, when I start a problem, I like to write the information given underneath the correct chemical formulas. So here it says I have 79.1 grams of zinc and 68.1 grams of hydrochloric acid. And it says to identify the limiting and excess reactants and how many grams of hydrogen can be formed. So even without the question, identify the limiting and excess reactants, I can recognize this as a limiting reactant problem because I'm given information about both of our reactants. And so far in stoichiometry, we've only ever been given information about one reactant and maybe sometimes a product, but never both reactants. So when I see information given about both reactants, I know the first step should always be to identify the limiting reactant. So how do I identify the limiting reactant? First step is to find the number of moles of each reactant. So I'm going to think about my zinc. And my zinc, I have 79.1 grams, and I'm going to convert to moles. And the molar mass of zinc is 65.39 grams. And when I do 79.1 divided by 65.39, I get 1.21 moles of zinc. And now let's do the same thing for my hydrochloric acid. So hydrochloric acid, I have 68.1 grams of hydrochloric acid. And the molar mass of hydrochloric acid is 1.01 plus 35.45, which is 36.46 grams. So when I do 68.1 grams of hydrochloric acid divided by 36.46 grams, I get 1.87 moles of hydrochloric acid. Now at this point, I find it very important to label what these numbers mean. So what these numbers mean is this is the same number that's given to me in the problem. This is what I have of each of these reactants. And all I did so far is convert to moles because grams aren't our equivalent unit in chemistry. It's moles that we can compare. We can compare moles to moles. We can't compare grams of one thing to grams of the other because those aren't the equivalent units. So our first step is to figure out the number of moles. But so far, all I've done is compare the moles of, all I've done so far is convert the grams of zinc to the moles of zinc. So this is still just how much zinc do I have? 79.1 grams of zinc is 1.21 moles of zinc. And 68.1 grams of hydrogen is just 1.87 moles of hydrogen. So now what I need to do is I need to determine how much of the first reactant would be needed to use all of the second reactant. And I'm going to do this with my mole ratio. Okay, so I'm going to start, let's just do zinc because that's the first reactant, but really you could do this with the other one too. So I'm going to start with my moles of zinc and use my mole ratio to figure out how much hydrochloric acid is chemically equivalent to that many moles of zinc. So my mole ratio from the balance problem is 2 moles of hydrochloric acid is 1 mole of zinc, because remember, those are just my coefficients. And so when I take the 1.21 moles of zinc and I multiply it by 2, I get 2.42 moles of hydrochloric acid. Now, at this point in the problem, I now have two numbers that have to do with hydrochloric acid, right? I have this number and I have this number. And what I just figured out is compared to zinc, how much hydrochloric acid do I need? So I'm going to label this as need. Okay, so if I wanted to use the entire 1.21 moles of zinc, it would require 2.42 moles of hydrochloric acid. So if I have 1.87 moles of hydrochloric acid, but I need 2.42 moles, my question I want to ask myself is, do I have enough? And the answer here is no. I do not have enough hydrochloric acid because my have is less than what I need, right? 1.87 is less than 2.42. So I'm going to run out of hydrochloric acid. So what that means is I just determined my limiting reactant. My hydrochloric acid, I'm going to run out of. I'm not going to have enough of it. It's going to limit my product. So that is my limiting reactant. So now on my notes, I can then label that that's my limiting reactant. And because in this equation, you can see I only have two reactants. I only have zinc and hydrochloric acid. If hydrochloric acid is my limiting reactant, that means that zinc is going to be my excess. That's what I'm going to have left over of after this reaction is complete. So now that I've determined my limiting reactant, I can go back and answer the question that it asked. How many grams of hydrogen can be formed? So in order to solve any of these types of problems, we first have to figure out what the limiting reactant is and then convert to grams of product. So if I go back and I look at what it was in the problem that I had of hydrochloric acid, I'm going to start with that 1.87 moles of hydrochloric acid. I could also go back to the original problem and start with the 68.1 grams, but because I already converted it to moles, I might as well use that moles number. What I can't start with is I can't start with the need. I can't start with that 2.42 number because I don't actually have that much hydrochloric acid. I only have 1.87 moles. So I'm going to start with the 1.87 moles of hydrochloric acid, and I'm going to convert to grams of product, which in this case, I was asking specifically about hydrogen. So I'm going to convert from moles of hydrochloric acid to moles of hydrogen. And my mole to mole ratio comes from the coefficients of my balanced equation, which in this case is 1 to 2. And then I'm going to convert to moles of hydrogen using the molar mass. And because hydrogen's diatomic, it's 1.01 times 2, and that gets me 2.02. And so when I do a little bit of calculating, then I figure out that I am going to make 1.89 grams of hydrogen in this problem. And so that answered our original question. We determined our limiting reactant to be hydrochloric acid, our excess was zinc, and then we figured out with our hydrochloric acid being limiting, how much product can we make, and that's 1.89 grams. Now, a follow-up question I could ask has to do with how much zinc is left over. So let's picture what happened in this reaction. I had some zinc. It's a metal, it's silver. I throw it in a test tube and I add some hydrochloric acid. And what's going to happen is we're going to make some hydrogen gas and we're going to have some zinc chloride in the test tube, but we're also going to have leftover zinc in that test tube because the zinc, we've got stuff left over. And so what I might ask you is, well, how many grams of zinc is left over at the end of the reaction? So we have to first figure out how much zinc reacted. Okay, so in order to do that, I am always, once I determine my limiting reactant, going to start with my limiting reactant. So I'm going to start with the half of my limiting reactant, and I'm going to convert to, it asks for grams. So I'm going to convert to grams of my zinc, which is my excess in this case. So let's go back to that same. What did I have of the limiting reactant? I had 1.87 moles of hydrochloric acid. And so let's convert to grams of zinc. So we're going to do moles of hydrochloric acid, convert to moles of zinc. And that's from the coefficients of our balanced equation, which is 1 over 2. And then I'm going to convert to grams of zinc using the molar mass of zinc, which is 65.39 grams. And that's going to get me 61.1 grams of zinc. So what does that number mean? That number means this is how much zinc I needed to complete the problem. So the equivalent of my half of hydrochloric acid is 61.1 grams of zinc. Now, what I need to do with that is I need to take how many grams of zinc did I have, subtract how much I need, and that's going to tell me how much is left over. So if I go back to the beginning of the problem, I had in the problem 79.1 grams of zinc, but I only need to use 61.1 grams. And therefore, that means I'm going to have 18 grams of zinc left over at the end of this reaction. And what this tells me is that I did this problem right. If I would end up with a negative number somehow here, that means that perhaps hydrochloric acid wasn't my limiting reactant. Perhaps zinc's not my excess, or maybe I had a molar mass wrong somewhere along the way. So having a positive number here at the end is a good indication I did it right. So we have this reaction. We put in 79.1 grams of zinc, and we put in 68.1 grams of hydrochloric acid. The reaction's going to go, and it's going to make 1.89 grams of hydrogen gas. It's going to use all of the hydrochloric acid, and at the end, what I'm going to have left over at the bottom of the test tube is going to be 18 grams of zinc. And that's the end of our first example. Let's try another example of limiting reactants. Here I have magnesium and oxygen reacting to form magnesium oxide. First, let's start by balancing this equation. Because oxygen's diatomic, but the formula for magnesium oxide is a 1-to-1 ratio, I know that I'm going to need to put a 2 in front of magnesium oxide to balance my oxygens. But now I need to put a 2 in front of magnesium in order to balance my magnesiums. Now that I have my balanced equation, let's go ahead and read the problem. It says that 5.42 grams of magnesium react with 4 grams of oxygen. Identify the limiting and excess, and then how many grams of magnesium oxide were formed. Now again, in this problem, even if it didn't ask me to identify the limiting and excess reactants, I'm going to know that I need to do this because when I look at the numbers given to me in the problem, it gave me information about both of my reactants. And that's a good indicator. It's a limiting reactant problem. So step 1, I'm going to start with magnesium, and I'm going to convert my magnesium in grams to magnesium in moles. The molar mass of magnesium is 24.31. And what this tells me is that I have 0.233 moles of magnesium. Let's do the same with oxygen. So for oxygen, I have 4 grams, and I'm going to convert to moles. And because oxygen's diatomic, it's 16 times 2, so that's 32 grams. And 4 divided by 32 gets me 0.125 moles of oxygen. So again, I like to think, what do these two numbers mean? This is, according to the problem, how much I have of each reactant in order to perform the reaction. What I need to now figure out is which of these is going to be limiting. And in order to do that, I'm going to start with the moles of one of them. And because magnesium's first, I'm just going to start with the magnesium, but you could start with the oxygen. So I'm going to convert from moles of magnesium to moles of oxygen to figure out if I have enough oxygen. And from my balanced equation, my mole ratio is 1 over 2. And so if I do the 0.223 divided by 2 with sig figs, I get 0.111 moles of oxygen. And this, remember, this is what I need. This is my equivalent number of moles. If I want to use all 5.42 grams of magnesium, if I want to use all the 0.223 moles of magnesium, it would require 0.11 moles of oxygen. So at this point, I want to ask myself, do I have enough? Okay. If I look at this, I have 0.125 moles of oxygen. I need 0.111 moles of oxygen. And so I do. I have enough because what I have is greater than what I need. So because I have enough, yes, oxygen is my excess reactant. In order to use all of that magnesium, I have more oxygen than I need. And so that means oxygen is my excess. And again, because this is only a two reactant problem, if oxygen is my excess, then magnesium is my limiting reactant. And so even though it's just the other thing is my limiting reactant, I do like to label that. Okay, so now that I have this information, now I can go back and answer the question, how many grams of magnesium oxide are formed? Now remember from our first example, in order to solve this problem, we're going to start with our limiting reactant. And we're going to make sure we start with the number is what we have of our limiting reactant. And we're going to convert to the grams of our product, which in this case is magnesium oxide. So I want to make sure I go back and start with the right number. I want to start with the half of my limiting reactant, which is magnesium. So I'm going to start with this I'm going to start with this 0.223 moles of magnesium. And I just want to do a gram to gram of my product, which is magnesium oxide. So I'm going to do my mole ratio of magnesium to magnesium oxide, which in this case is 2 to 2. If you want to reduce that to 1 over 1, go right ahead. And now I'm going to convert my moles of magnesium oxide to grams of magnesium oxide. Now magnesium is 24.31 and it's got one oxygen, which is 16. So my molar mass is 24.31 plus 16, and that's 40.31 grams. And then I'm going to do a little calculator magic. And what I find out is that in this reaction, I'm going to be able to produce 8.99 grams of magnesium oxide based off of my limiting reactant of magnesium. So again, let's think about what's happening in this reaction. I'm going to have some magnesium. I'm going to light it with the Bunsen burner, and because there's a lot of oxygen in the air, I have some excess oxygen, right? And so then this says I should make 8.99 grams of magnesium oxide based off of that 5.42 grams of magnesium I started with. So now it's asking a follow-up question that if I only made 6.5 grams of magnesium oxide, what's the percent yield? Well, remember our percent yield equation. Percent yield is what did I actually make in an experiment divided by how much should I theoretically make, what's the maximum amount of product I should make, times 100%. So I made 6.5 grams and I was supposed to make 8.99 grams. And then I'll multiply times 100. And 6.5 divided by 8.99, since 6.5 is only 2 sig figs, I'm going to round to 2 sig figs, which just happens to be the nearest percent. So this is a 72% yield. Another follow-up question that I could ask is if I wanted to make more, and I wanted to make sure that I used all of my excess, which was oxygen, how much more magnesium would I have needed? So the first thing that I want to do is I want to start with my excess, which was the oxygen, and figure out what is the equivalent amount of magnesium that I need. Now, I could start with that 4 grams of oxygen, but remember earlier in the problem, I already found the number of moles that that was equivalent to, and that was 0.125 moles. So to save myself from doing the same step again, I'm just going to go ahead and start with that 0.125 moles of oxygen. And let's figure out what is the equivalent number of moles of magnesium. So I'll do my mole to mole ratio. My mole to mole ratio is 1 to 2. And then I'm going to convert to grams of magnesium, which is 24.31. And I figure out that is 6.08 grams of magnesium. Now, again, I can do all of these problems, but it doesn't help me if I don't know what that answer means. And what that answer means is if I wanted to use all of the oxygen, how much magnesium would I need? And I would need 6.08 grams of magnesium. And the question says, how much more limiting reactant would I need? And so what I'm going to do is I'm going to do what I need minus what I have. And what that's going to tell me is how much more did I need to complete this problem. So I needed 6.08 grams of magnesium, but I only had 5.42. So if I wanted to use all of the oxygen in the problem, I would have needed 0.66 grams more magnesium in order to use all of that oxygen.